Yes, good morning, students. I hope we are all doing fine. And we are going to continue with our classes. And under operating systems today, we'll talk about main memory, memory management. And we know that main memory is what we refer to as a random access memory. And for a program to become a process, the program has to be loaded into main memory and allocated its necessary resources. So we say a program is a what? A passive entity, and a process is an active entity. So we'll be looking at the key points of the things we'll be looking at. We'll look at the background, look about, we'll look at swapping, and we'll talk about contiguous memory, which I spoke about in arrays. Then we'll look at segmentation, paging, check out the structure of the page table. Then we'll briefly look at the Intel 36 and Intel 64-bit architectures and the ARM architecture. Okay. Now, our objective is to discuss various memory management techniques, which a few of them are paging and segmentation, and we provide a detailed description of ways of organizing memory hardware. Now, this course is called it's called Operating System Concepts. So basically, it gives us the insight in case we are part of a team or we intend to develop an operating system, the things that are involved and what must go into developing the operating system. So it gives us the clear insights into it. So a program must be brought from disk into memory. Yes, I've explained that. So you have the passive entity and the active entity. And a CPU can only directly access registers, cache, and main memory. That is it. The CPU cannot directly access your secondary storage. It cannot directly access your external drive. That's your flash drive. So these are the three things the CPU can directly access. And the cache usually sits in between the registers and what? The main memory. Okay. Now, there must be protection of memory. And how do we protect memory? We use addresses because usually when you see the main memory sees unit of addresses and a read request. So the unit of addresses is the maybe where the data is supposed to be fetched from and where it's supposed to be sent. And you also have the request whereby it could be a read operation or a write operation. Now, in order to protect these addresses, we have something called the base register and the limit register. And these are used to ensure that one process's address space does not spill over into another process's address space. And it also helps to protect the system softwares that are placed in the system and prevent users from veering into addresses that are restricted. Yes. So it can be able to trap it and provide you with an error message. So we first need to make sure that each process has a separate memory space. That is true. So usually we can provide this protection by using the base and the limit register, as I've discussed. So the base register holds the starting address of that process. Then the limit register will hold the size of it. So if, let's say, the size is maybe 100, so the limit register will hold the base register address plus the size. So plus the size, it will give you eventually the starting address and the ending address. So a pair of base and limit registers define what the logical address spaces. All right. So CPU must check every memory access generated in user mode to be sure it is between base and limit for that user. And if the base register holds, let's say, 300040 and the limit register holds 1209000, then the program can legally access all addresses from 3000040 through 420940 inclusive. So meaning 420940 is inclusive. Now, if you go and add 1209002 to 3000040, you're going to get what? 420940. So the 42090 is going to be held in the limit register, and the 3000040 is going to be held in the base register. So you're able to know the starting address and the ending address. So let's look at the diagram here, and you can see. So for a process, the second process, the one that is in the middle, you can see that there is a base register and there's the limit register, and the limit register is the ending address. Like I told you, the limit register contains the contents, or the address of the base register plus the size, okay, plus the size. So when you add it, you know the limit of the addressing, and you can determine the address range for that process, meaning that process can be able to access any of these addresses in between. So protection of memory space is accomplished by having the CPU hardware compare address generated in user mode with the registers, which is the base register and limit register. So any attempt by a program executing in user mode to access OS memory or other users' memory results in a what? Trap. I've just said that. Okay. So this scheme prevents a user from accidentally modifying the code or data structure of either the OS or other users. So there you have it. So you have CPU address. Then if it is yes, you have the base address which comes in, and the base address is greater than or equal to. If it is yes, greater than or equal to, then we'll say if the base plus the limit. If it is greater than or equal to, no, if it is less than, then we can go and access. But if not, there's a trap, and there's an addressing error. Okay. So yes, so we look at the base address. So we are saying that the address we are trying to access, if it is greater than the base address, then yes, we've cleared the starting address. Then the ending address, if the base address plus it's less than the base and limit address, then yes, we can access the memory. But if the address is greater than the base address, and if the address is less than the base address, which is meaning it is outside the range, and it is still less than the base and limit address, which is in the limit register, meaning it's not within the range, then no, a trap is created and it gives you a message saying addressing error. So a program must be brought into memory and placed within a process for it to be run. So we are looking at address binding. So there is input queue, collection of processes on a disk that are waiting to be brought into memory to run the program. And user programs go through several steps before being run. Now, address binding of instructions and data to memory addresses can happen at 3 different stages. Okay. We have compile time, load time, and execution time. So if the memory location known a priori or absolute code can be generated, you must recompile code if starting location changes. I'll explain. Load time must generate relocatable code if memory location is not known at compile time. Execution time. Binding delay until runtime if the process can be moved during its execution from one memory segment to another. Now, look at it this way. Imagine you go to a ticket agent and you intend to buy a ticket to travel to, let's say, Finland. Imagine the situation whereby when you buy your ticket, we are looking at compile time. When you buy your ticket is given, but the seat you're going to use is not given to you. It is given to you on the day you arrive at the airport. Then they'll tell you you are at row 67A. So that is compile time. So compile time is saying that after we compile, we can generate the what? We can bind the address. Okay. Now you look at load time. What do we mean by load time? Imagine you're going through the same process, right? And you're going to purchase the ticket to travel to Finland. Now, when you get there, you purchase the ticket, but you are not given your seat number. On the day of departure, you go to the airport and you're still not given your seat number. You see? And your seat number is given to you once you are boarding the plane. Okay? Load time. Then you have execution time. With execution time, the seat number is given to you exactly when you make a purchase of the ticket. Okay, we'll look at it further. So we have compile time and address binding. We have compile time now. You see, if you look at Java, we use compilers, and you notice that we compile the codes before we run the codes. Okay, so when you compile the codes, say if memory location is known, you see, absolute code can be generated. So during the compile time, that is when the the address is or location is generated, and this says load time. So there's a difference between compile time. When you load the program, that is load time. When you're loading the program into memory to be able to access the compiler, and this one says compile time. Now after that, there is execution, when you're executing your problem, and when you execute the problem, that is when the address is binded. Okay, so processing of the user program. So you have the compiler or assembler, that is compile time. So the load time deals with the linkage editor and the loader. So you'll see here that on the left it says other object modules, and you see system libraries. So basically, when you compile your program, there must be loading, because there are sometimes some functions that are being called in there, but the functions are not explicitly stated. So it's in the library. So it has to do what? It has to link to load these functions so your program can compile and eventually what? Execute. So that is load time. And execution time is dynamic linking, and it is the runtime to execute the program. Okay, so take note of these three different things. Now, there is a concept of logical address space and physical address space. Yes. Logic address is generated by the CPU, and is also referred to as what? Virtual address. So note that down. And the physical address are seen by the memory unit. So for instance, secondary storage has a physical address. Our random access memory has a physical address, yes, but our things like our registers, cache, they deal with what? Logical memory addressing. Yes, they deal with logical memory addressing. With our random access memory, we said that it is what? It is volatile. The contents of it goes is cleared once the system goes off. Yes. However, the dividing of the memory is physical, so it always has these kind of locations in there, right? So logical and physical addresses are the same in compile time and load time, address binding schemes. So logical is virtual, and physical address differ in execution time, address binding schemes. So logical address space is a set of all logical addresses that is generated by either the CPU or the program. And the physical address space is a set of all physical addresses generated by a program. Hardware devices that run on time maps virtual to physical. Yes, it maps virtual to physical. Now look at it this way. In main memory, right? Because we know that our registers and our cache can only hold so much, okay? So what ends up happening is that sometimes whilst the CPU is executing, it might need a certain data, or it might need certain library link, but it cannot be found in the registers and it cannot be found in cache. So that's when we call it a cache miss. So it has to go into main memory and go and find it. Now how is it able to locate it? Because of what? The table. So the table indicates that this thing is located at this address. So it maps the physical and the logical addressing. So the physical addressing in main memory where the file or the data you need is located. Then once it is brought into either cache, it is mapped to the same address. So in cache, maybe you have this logical address 3F2999, but it maps to a physical address of 46ABC. Just an example I'm giving. All right. All right. So to start, consider simple schemes where the value in the relocation register is added to every address generated by a user process at a time and is sent to memory. So base register can also be called the relocation register. And user programs deal with logical addresses. It never sees the real physical address. Execution time binding occurs when reference is made to location in memory. So logical address bound to physical address means there's a mapping there. So let's look at now instead of base register, we are saying when it comes to address binding, we are calling it what? The relocation register. So in the CPU, we have a logical address that is located at address 346. Okay. So at address 346, um, in our location register, which is indicating somehow the size, because our relocation register, because now we are trying to map the logical address with the physical address. Okay. So in our relocation register, we have what? 14,000. Okay. So what is going to happen is the memory management unit will perform an addition. It is going to add the logical address to the relocation register value that is in there. So once it adds it, it knows that yes, so at physical address location 14,346, I will find the physical address for that data or that file on on memory. Okay. In simple words, let's say I have a file named ABC, right? And I've loaded ABC into memory. I've loaded ABC into memory. And I've loaded ABC into memory. Um, it has to move from memory into the cache memory. So once it goes into the cache memory, it allocates it an address of 346. So to be able to map it directly in the mapping table, we know that the value that is in the relocation register is added to the logical address, and we know that exactly the physical address of that is 14,346. So all routines kept on disk in relocatable load format. Okay. All right. So this is a linker. We have static linking and we have dynamic linking. So look at the program on your left. So this program, once it is compiled, this is what we get. We get our byte code, which are zeros and ones. Now it has to call a function called one. And how is it going to call the function? It's right here in the library, one. So what happens is that this program will move, and it is going to move to the linker. So once it gets to the linker, then the linker will contact the library, and the library will do what? Will load that function one, and you'll be able to execute the program. So that is static linking. Okay, that is static linking. So this is linking, static linking. Then we have dynamic linking. So with dynamic linking, the library is here. So memory address where one function is loaded included in final execution file. So it adds it to the final execution file. So address of one function in memory, that is 0x2EA126. So the one function is, and you see it in libraries on your right, okay? So static linking. System libraries and program codes combined by the loader into the binary program image. And dynamic linking postponed until execution time. Note that. So a small piece of code called a stub is used to locate the appropriate memory resident library routine. And the stub replaces itself with the address of the routine and executes the routine. So the OS checks if routine is in process's memory, if not in address space. So dynamic linking is usually useful for what? Libraries, and system also known as shared libraries. Now we look at swapping. A process can be swapped in and out of memory. Yes, we looked at it in virtual memory. So we know that when we say virtual addressing, we are talking about what? Logical addressing. Yes, so can be swapped in and out. So a process can be swapped temporarily out of memory to what? Backend store, and then brought back into memory for continued execution. So the backend store is the fast disk large enough to accommodate copies of all memory images for all users, and it must provide direct access to these memory images. So you have the rollout rolling. So the swapping variant used for priority-based scheduling algorithms. Okay. So lower priority process is swapped out, so higher priority processes can be loaded and executed. And a major part of swap time is transfer time. So the total transfer time is directly proportional to the amount of what? Memory swap. All right, so does the swapped out process need to swap back in to same physical address? No. You see, the physical address, when it is swapped out, it is placed in its physical address. When it's swapped back in, it is placed into its logical address. So the logical address, the relocation register, is able to have a table that is able to map it. So for the physical address, yes, when it swaps out, it goes into that location from the backend store. Um, yeah, so it depends on address binding method that you're using. Okay, so modified versions of swapping are found on many systems, and swapping normally disabled on some of these systems. Okay, so there you go. You have your backend store. So you have your OS in the user space. So you swap out and you swap in. Why do we swap out and swap in? Because if we have a cache miss, we're looking for a file or data, and we don't find it in cache, then we have to come into main memory. So if we don't find it in main memory, then there has to be a swap out and swap in, because we have to conserve memory space, use our memory space judiciously. All right. Okay. We know about context switching. That is switching from one, whilst one process is executing, we switch from one to the other. So if next process to be put in CPU is not in memory, needs to swap out a process and swap in target process. So context switch time can be what, very high. Yeah, it is an overhead cost. All right, so we will pause here because this slides is about 40 long. We will pause here, then we'll take a part two. So today we're going to discuss about what we've done right now. I don't want to overload you guys with all this information, but we'll take it one step at a time. Okay. So we'll meet tonight and we'll discuss. Okay. Have a good day.